looks like we're up and running. I got to send this link again because the first one dropped out on me. So I'm going to send a second link to the Blackboard announcement here, and we'll try this again. All right. Hopefully this is getting out to people, and hopefully you can see what we're doing. If you're watching this later, the link failed, and I'm putting up a new video link. So starting over here. Hopefully this works. Looks like it's running live now. So I'm going to give this a try. And position this. We're going to look at systems of equations here. I'm talking to myself. We're going to look at systems of linear equations first of all, and then some nonlinear equations. I'm going to try to position this thing so we can see what I'm looking at. All right, so linear equations look like this. You got only number terms and variable terms in there. So we're talking about two variable systems. You could do similar stuff with more variables. We're not looking to go into more variables. We're going to do this just with the two variable stuff. So we're looking at equations that have an x term and a y term and a number term. So a linear system would look like that. 5x plus 3y equals 24 is an example of a linear equation. Now a system of equations means we're going to have we going here? Okay, looks like it's working. The system of equations is going to have more than one equation that both have to be true. So if you have 5x plus 3y equals 24, there's a whole line of points that would make this true. Right, that could go through 3, 3 because 15 plus 9 is 24, or it could go through 0, 8 because 0 plus 24 equals 24, or so on. That's a whole line. We know how to graph lines. So that's the graph of an entire line of points. A system is going to say this has to be true, and you can link them together with some symbol if you want, but the other equation is also true. So like x minus y equals 11. That would have a different set of equations, set of solutions that work there. And in order to be a solution to the system, both of these things would have to be true. So we're looking at algebraically, how can I find a solution that works in both of these equations? If both of those are true, then what can I do with that to try to find the x and y that make that thing work? Solving that means finding the ordered pair that makes both of those things work. Nice thing is these things have a picture to them also. We're going to work with them algebraically, but you also have a nice picture because we know how to graph these things now. We know how to plot points and draw graphs. So if 5x plus 3y equals 24 has these points, goes through 3, 3, and 0, 8. And you got a line like this, corresponds to that equation. And then I can do one that corresponds with x minus y equals 11. I'm going to go ahead and put this in y equals form. Rearrange it because we're used to graphing things in that form. I think that's y equals x minus 11. So that's a slope of 1 and an intercept at negative 11. So that's way down here. With a slope of 1, it's going to go out here somewhere. And you can see on the picture, there's probably one point out there, exactly one point where these two lines intersect. That's exactly one ordered pair that works in both of these equations. That's what we want to find. That solution would be that point on the picture. But drawing the graph is a lot of work, and we're actually going to solve these things algebraically without having to do that much work. There's a couple of techniques that work on these things. Looks like we got a couple of people joining, which is good. I'm glad you all found us after the mix-up with the video, but we're up and running now. Certainly can drop in some questions if you want, but we're on a new topic here. Finding solutions like this. So working with it algebraically is less work than graphing it. We don't have to worry about all of those other points. We just want to find the one key point that makes both of those things true. So here's a couple of thoughts about that, and we're going to develop a couple of techniques. And then when we get some techniques that work on this, we're going to think about how we can use those techniques on nonlinear systems. That means we can have more complicated equations, still dealing with a system of two equations and two unknowns. But maybe that throws in maybe x squared, y squared, or x times y, or 3 over x, or something more complicated than that, than just linear terms. That's what we got to think about next. So we're going to set that aside for a while. We're going to get a couple of methods that work on linear systems, and then we'll come back and try out some nonlinear stuff, see how our methods apply to that, see how we can do solving more complicated stuff. All right, so I'm going to get some space to work through a system like this. We got one good example there I'm going to try to work through. This thing. I'm going to take that example that I wrote down, and I don't know what the solution is, but we're going to find it. 5x plus 3y equals 24, and x minus y equals 11. Notice the way that I've written them, I kind of have this kind of standard form where the x term and then the y term and your number term is on the other side. That's what they called standard form for these lines. It was never that useful for graphing, but this form is going to be really useful for us now, working on these systems. Thought process on this that I want to try to get across quickly here in the introduction to this. If that's equal to 24 and that thing is supposed to be equal to 11, can I do this now? Can I just add these things up? 5x plus 3y plus x minus y, that would be 6x and 2y if I add all that up. Would that be equal to 35 then? Is that true? That's a little thought right there. But yeah, if this is some expression and the values of it came out to 24, and if this was the same x and y here, and that came out to 11, then I can combine the x's, I can combine the y's, and that should come out to 35. That's true, but it's not useful. Okay, that doesn't really help me to figure out what x or y are, because it's just another equation with x and y and number term. I still don't know any of the numbers on that. So, but this idea is true, that if you have two equations, you can add them up and get the result right there. That's a useful idea. So adding equations is useful, but we have to manipulate it to actually do us some good here. We have to mess with them. We have to mess with them so it'll help us out. So instead of adding them as they are, let me rethink this a minute. I'm going to write down the whole thing again so I can work with this and actually get somewhere this time. If you remember doing these before, well, we didn't do them this semester. So if you remember them from your past algebra work, that's a great head start. We're going to throw in the nonlinear systems, which isn't traditionally an algebra topic that they spend much time on. So we're going to get a little variety that way, and also give us some practice with graphs and equations that were more complicated that we did. So it's review. It's nice review there also. But I want to use this idea to do some good. What happens if I do this? I'm going to keep the first equation the same. And I'm going to multiply by 3 down here. I'm going to take that whole equation and multiply every term by 3. Now, I can multiply both sides of an equation by something. It does not change the solutions to it. It doesn't change the values that work in there if I multiply everything on both sides by 3. So that's equivalent. But see, now I've set it up so that I have nice opposite terms right there. I've constructed opposite terms. And the idea is now I can eliminate something by adding these things up. When you have opposite terms there and you add these up, 5x plus 3x is 8x. 3y and a negative 3y isn't going to add up to anything, right? That's a 0. And that's supposed to equal, what do we got, 57? So that really helps me. That's actually helpful. I eliminated a variable on that. So this is using elimination. If you can mess with your equations to get some opposite terms for one of the variables, then adding them up will eliminate that term. That works nicely if you have nice like terms like this. That'll help us on any of these linear systems. That'll help us on some nonlinear systems, we'll see. Once I get down to this, now I know what that is. X has to be 57 over 8. That's the value of X that works. I still need to know what Y is, so I would still have to come back somewhere and figure out Y. But once you know one of the numbers, pretty easy to solve for the other. So now we come back to here. And if X minus Y is supposed to be 11, I'm just using one of these equations. 57 over 8 is the X that works. I need the Y that works with it, so I'm just going to solve this out for Y. 57 over 8 minus Y equals 11, so Y, if I move the, or add Y to this side and subtract 11 over here, I can get the value of Y that works. 57 over 8 minus 11. All right, that's a little fraction work, but I'll write this out now. That's a common denominator there, so I got negative 31 over 8. Both of those are parts of the solution right there. So that's the solution. That's the ordered pair that works. I could write it like we usually do for ordered pairs for plotting points. We write X comma Y. That's the ordered pair that works. It's 57 over 8 and negative 31 over 8. That's a positive X and a negative Y, which if you look back at the rough sketch that I did, that looks right with the picture here that I'd have a positive X and a negative Y down here somewhere. That's pretty close to what we're looking at there. So that looks right. And that method will work nicely on all of the nonlinear systems, because if all you're allowed to have is X terms, Y terms, and number terms, then these are going to be like terms. It's real easy to manipulate them to make them opposites. We might have to mess with both equations or something, but we can construct those opposite terms easily. So I'm going to do more examples on that thing. And we'll throw in some other kinds of equations also. So after doing all that fancier stuff with exponentials and logs and all that, we're back to fairly simple equations and just dealing with them in a little different way here. So some of these come out of chapter 7 in the book. The linear systems are in here. We're only doing the basic kind here. And then we're going to jump to nonlinear systems, which is not in your printed textbook, but there is some of them in chapter 9 in the online version of the book. If you're using the XYZ homework thing, you have free access to now. You can get into there, but it's really not that useful to dig into the book for that because it's only part of one section in the book. We're just going to throw some examples around on it. I don't think I added them to the homework. I'll have to check that. But linear systems are in 7.1 in the regular book. I'm going to do some out of there. So what we were just doing is called in this book the addition method. And the idea is you can add equations and it's helpful to add equations if you can make these opposite terms on one of the variables, either one of the variables. So here's another example on that. Then we'll talk about another method we can also use that I want to introduce. This one comes from 7.1, number 13. It's actually out of the book. This one equals 16 and this thing equals 11. Adding them up like this wouldn't help me, but if I can construct opposite terms somewhere, then it will help me. And I like to work sideways on this. I like to make the opposite terms because I want to add them up and get something useful here where I can eliminate something. Now 5 and 3 I could mess with, but I like the 2 and 4 right here. That's a little easier numbers because I can, if one of them's 4, I can easily make this one into -4. We have to do this by multiplication. We have to multiply every term by a number to create those opposite terms. We could do both equations, but this way I can get away with just doing this one. If I multiply by -2 in that first equation, then that turns into -4x plus 10y equals -32. And I can keep this one the same because I've got my opposite terms now. So that still equals 11. Now I got the opposite terms that I like to have there. So my addition will eliminate the x. That doesn't contribute anything. 10 plus -3 is 7y. -32 plus 11 is -21. So this comes out to a fairly nice number here. That's part of the solution. Now the temptation here is to feel like we're done because we got y equals -3. That looks like the answer to something because we're used to one variable equations. We got to remember we're looking to make these true. So knowing the y value is not enough to make that come out to 16. And that 11, I need the x value that goes with it. So I'm going to have to go back and get the ordered pair somewhere. Now it doesn't matter which one of these equations I use. They're the same x and y everywhere. So if y has to be -3, I can drop that in anywhere up here and find out what works. So I'm going to use this one that's on the bottom here. It says 4x minus 3y equals 11. And I know y is -3 now. So I can drop that in. -3 times -3 is 9. So 4x has to equal 2. So x is 1/2. That's the value that goes with it. Now you can check that right here. We got 1/2, comma, -3. X is 1/2, y is -3. That's the ordered pair form of it. Should work in both of these. If x is 1/2 and y is -3, then I get 1 plus 15. That adds up to 16. And in the second one, that's 2 plus 9 equals 11. Sure enough, that works in both equations. That's the one point where these things cross, and that works out great. Now, I want to think about a second method on this. I'm going to try to introduce both methods today, and then I got some time to work on these things next week. This is really the topic for next week and leading into the final. So I'm going to introduce both of the methods, and then we'll see how they apply to these nonlinear systems a little bit. We have all of next week to work on this stuff. So we'll get some of these in. And then along the way, we are practicing for the final. I want everybody to get your old tests. If you got your old tests and go back through them in the final, except for the systems problems, the final is going to be very similar to what you've been tested on already. So we're going to kind of assemble all that together and have one big test with a little bit of each topic on it. So looking back at these earlier tests is pretty important. The linear, the equation stuff, we're spending a lot of time on that within this context. So here's another method that also works nicely on these things that will extend better to the nonlinear systems. We get a second method called the substitution method. It's pretty useful whenever you're dealing with more than one variable. Think about these things the right way. So if I have a system still linear equations, this one's 6x minus y equals 10, bunch of numbers that could work there, but we're also supposed to satisfy this one, y equals negative 3/4 x minus 1. This is kind of convenient for a substitution because I have this big expression that's equal to y. Now, you know you can put these in y equals form or x equals form if you move things around. We can solve for a variable in these things. This one's already done. We have what we want to start with here. Hopefully stop the sneezing now. But the goal for the substitution method is to get an expression it's equal to one of the letters and then substitute it in. Really persistent sneezes. Okay. Y is supposed to be equal to this thing. So in my equation, 6x minus y equals 10. Well, if y is equal to negative 3/4 x minus 1, then I can substitute it in like that. That whole expression goes in place of y. That's where your substituting takes place. We're going to substitute that in. Now I just have an equation with x. It's a little bit long, but it's just a linear equation in x. If I get rid of the parentheses, I like to get rid of the most complicated thing first. So I'm getting rid of the parentheses, and that subtraction applies to both of these. So that makes them both plus. Don't really like fractions going around. If you recall, when we had equations with fractions in them, we might get rid of the denominator by multiplying everywhere by that. So I can make this easier to work with by doing times 4 everywhere. That's my only denominator. And if I multiply each of those things by 4, it doesn't change the solution of it. It's just going to look easier to handle. 3/4 times 4 is 3. All of these things get multiplied. Now I got a simple equation like that. Well, pretty simple. Solve for x and that. Those will combine. I gotta try to stay on screen here. Subtract 4 from both sides and divide. 36 over 27, I can simplify a little bit. That's 4 over 3. I can take the 9 out. So I have a number, x equals 4/3. Number isn't good enough here, right? If you're solving equations, you should always check your answer. And if you got that habit going, or at least think about checking your answer here. If you got that habit going, then you're going to go back here and say, if x is 4/3, well, I don't know if that's going to work or not until I have the y that goes with it. I got to get that. All right, so I'm going to go back and substitute this in to see what the y has to be. We always solve for something first, and then we got to get the other one. That's kind of the pattern with either method here. So I'm going to go back to one of the original equations, but I already have what y equals here in terms of x. So that's a very natural place to do the find the y value since it's already isolated there. X is supposed to equal 4/3. So y should equal negative 3/4 times 4/3 minus 1. And that comes out pretty nice. That's negative 1 minus 1 is negative 2. So I got x equals 4/3. And y equals negative 2, or if you want to write that as an ordered pair, that's good. 4/3 comma negative 2 is the solution to the system. So that's the key to these things when we're talking about systems. The word solution is not just meaning a number here. The solution to a system would be an ordered pair. that makes both equations true. If we're talking about two equations and two unknowns, then we need both values that make both equations true. And that, if you follow the steps through and don't make any mistakes with all of that, the numbers that you get will work in both equations. Nothing weird should happen with that. We're just doing regular equation solving stuff. So the numbers that you get should work in both equations, and you can check that. Now, there's enough steps in all of that where it's really easy to make algebra mistakes along the way or calculation mistakes along the way. So you got to be careful with it. But the substitution idea is great. You can always get down to one variable. If you can do this isolating to get one variable isolated and get the expression that it's equal to, then substituting that into the other equation will get you down to one variable, something that you should be able to solve for from there. Now, graphing these things, you should remember how to graph these things. That's a nice thing to review here also while we're on linear equations. So what we did with them before was draw graphs of these things. So hopefully this is familiar and we can tie it together with what we're doing now. I don't need the picture to solve this and really help with the solution method, but it's another way to kind of line this up and to get a little review of what happened back here. We can graph these things since we know about slope-intercept form. We know this one has an intercept at -1 on the y-axis and a slope of -3/4. That's going over 4 and down 3. So it would be down here. Over 4 and down 3 is the slope of it. So it's going this way. That would be the graph of this equation. The other one, if I want to do slope and intercept on that, I'd have to rearrange that a little bit. So let me do that. I got -y equals -6x plus 10. And then divide by -1, I got 6x minus 10. So that's something with an intercept way down here at -10, but a slope of 6. So it's going over 1 and up 6. It'd be at like 1, -4 now. And then 2, 2 would be way up there. So we're going up this way. And your solution, that one point that works on both of them, is right there, a little bit past 1 on the x and some negative number for y, right? And you can look back down here and say, oh yeah, we got 1 point something for the x value, and we got -2 for the y. So that looks right with the picture there also. It should. We can get a little practice with graphs as we go along. Next week, we're going to do nonlinear systems. So we're getting a little practice with the graphs of lines here. Next week, we're going to get a little practice with the graphs of parabolas and circles and see a few other graphs for more complicated equations. Think about how to graph those a little bit more. And along the way, solving things out from that is going to take a few more techniques. We're going to have quadratics. We're going to use quadratic formula and factoring and stuff like that for solving equations there. So you mix in a few other stuff. Both of these methods work great with linear systems. If there's a solution to it, then either one of these methods will find it. Both of them are always possible because there really isn't any variety to this kind of problem. There just has to be x term, y term, and number term in both equations. There's different numbers going around, but there isn't anything really essentially different about these things. Now, exceptions to that you ought to be aware of. Or what could possibly go wrong. Right, I think I've mentioned this before, that anytime you get a method going around, you should ask yourself, what could possibly go wrong? And that seems like a bad omen now, but the process that we're going through, I just said it works on any one of these equations, but if there is no solution, if we have two lines out there that don't intersect at all, then something's going to go wrong with the system, with the approach right here to to tell us that there is no solution to it. So we do have to worry about that eventuality. If we have this kind of picture, talked about parallel lines a little bit. Now, these are two lines. If they have exactly the same slope, maybe this is going over 3 and up 2, and this is also going over 3 and up 2 every time. They're in a different place, and they're going at the same angle here, so they're never going to intersect. That means there's never going to be a point that works in both of those equations. So that might look something like, well, this equation would have to have a slope of 2/3, so it would have to be y equals 2/3 x plus something. But if you have two different intercepts, then they're going to be at two different places, and you're going to get a graph like that, parallel lines. There's no solution to that. I think this one's kind of obvious if it's written that way, because you're looking at this and saying y is 2/3 x plus 5, but y is also 2/3 x minus 2. Well, it can't be both of those things, right? So there's no solution to it. But they can hide a lot better than that. What if the equation looked like negative 2x plus 3y equals negative 6, and y equals 2/3 x plus 5? I bet if I started out with it written that way, you wouldn't notice anything was wrong with it. It looks just like that example that we just did. Starts off the same way. One of them's in y equals form, one of them's not. So it's set up nicely to do substitution. If I had to pick a method, I'm going to lean toward my substitution method. I have this expression. I can substitute in for y, so that's going in place of y. Put the container there, see what you get. What it looks like ought to work just fine. Let's see what happens. So it becomes negative 2x plus 3 times y, which is 2/3 x plus 5. I don't write it as y anymore because I have a name for it. And that gives me an equation that doesn't have any y's anymore. And I can solve for x, except, well, let's see what happens. 3 times 2/3 is positive 2. 3 times 5 is 15. I got a linear equation with no solution. I got 0x plus 15 equals negative 6, right? You can't solve that. There's no solution to that thing. So that's how we can tell there's no solution to this system. If there was an x that would work, we would have found it here, and there isn't. 0x equals negative 21 is not happening, right? You're not going to have an x value. So you got no solution to that system. And that's something similar will happen with either of these methods if you have that kind of situation with your system. All right, little time left, and I am going to throw in one of these nonlinear things just to get started on that process a little bit. So I'm going to grab one out of XYZ homework that covers one of these other things. And I'll remind us a little bit about some other graphs that we want to look at too. So first, nonlinear system. Linear system has to have only x term, y term, and number terms. Nonlinear system is going to have anything else going on. Here's an example. Now, if you remember what those graphs look like, we can get a lot more possibilities on this. We could do graphs of those kind of things. If you know a little bit about the graphs, you can kind of see what's happening on this and what to expect. You can solve the system without knowing about the graph. We can do it strictly algebraically, but it's really nice to have a picture to think about also. So if you remember the graph of y equals x squared. What does this plus 4 out here do? That was just going to move it up 4. So that's going to start at 0, 4 instead and have, just like the graph of x squared, one of these parabola things. So that was a basic quadratic graph. Looks like that. X squared plus y squared equals 68 is actually a circle graph. X squared plus y squared equals r squared was the basic form for circle graphs. So r squared equals 68, and that means the radius of the circle is 8 point something. What's the square root of 68? Well, let me approximate it. Square root of 68 is like 8.25. That's the radius of this circle centered at the origin. So I have a circle centered at the origin that goes out to 8.25 in all directions. This is a sloppy graph of it, but the radius is 8.25. So graphs of stuff like that get a lot more complicated, and where they intersect is a little bit more interesting. Right? Lines cross at one point. Curves like this could cross at more than one point. You can imagine graphs that don't intersect at all pretty easily, but you could also imagine graphs that intersect at a whole bunch of points. This one looks like it's going to have two different values, and they kind of look symmetric there, so we'll see what happens with that. Even if I didn't know anything about the graph, I can try to apply those other methods here algebraically to the system of equations. And I'll get through one of these today, and then we have a week to work on these things still and get some review along the way. So a little review of graphs. These equations now, I don't have the same kind of terms here to try to eliminate something. I'm not going to be able to turn this nicely into opposite terms because I don't even have, I have a y term here and a y squared term here. That's not going to work out well for elimination. But I do have this expression going on, right? Y is already isolated here, and I have this expression for it, so I can substitute this in for y. I got a squared to deal with then, but I can use the substitution method. So this one's set up nicely to use substitution. It's a harder way to do linear systems, usually, but it's much more useful with nonlinear systems because you don't necessarily have like terms lined up all over the place. You have various kinds of terms. Substitution is more versatile. So that turns this equation into x squared plus, use the containers here, that's going to be important. That's y squared, and y is equal to x squared plus 4. Parentheses very important there because we have to square that whole thing. We're going to have a complicated looking equation, but it's just an equation with x in it. Polynomial equation we should be able to solve just with x. So let's see what happens. I got x squared plus. That's x squared plus 4 times itself. All right, this step takes a little thought. So let me write an in-between step here. Remember, the squared's outside the parentheses. So that's this whole thing times itself. We have to FOIL that out. We get x to the 4th plus 4x squared plus another 4x squared plus 16. That's it. That's equal to 68. Now that looks long. We got different powers. We got squared terms and fourth terms and stuff going on. But it's a one variable equation. It's a polynomial equation. So our technique for these was to use the zero factor property. We want to get a 0 on one side and see if we can factor this. We hope so. Well, let's see. Well, I'm going to put this in descending order. I got a couple of like terms that go together. And then to get to 0, I have to subtract 68 from both sides. So I get negative, oh boy, 52. Negative 52. X to the 4th plus 9x squared minus 52 equals 0. I got that equal to 0 because I'm hoping it factors. So let's see. Here's a little review of factoring built in. Right, this is all nice stuff. Getting ready to take this final. I'm hoping I can write this in factored form, and then one of the factors has to equal 0. It comes down to looking at the number negative 52 and saying, is there two things that multiply to that add up to 9? And it turns out negative 4 and 13 add up to 9 and multiply to negative 52. So this middle term becomes negative 4x squared plus 13x squared. You see how there's built-in review of a whole mess of the algebra that we did early in the semester here thrown in, and we're using it in this context now. I like that about this course. Pull out what my factors are from the box here. Then I got x squared. I got 13 as a common factor that way, and I got x squared minus 4 this way. So I got these factors. 0. Still have squareds, so I got to think, can I factor this even further? And the answer is yes. X squared minus 4 factors into x minus 2 and x plus 2. That's a nice difference of squares thing. It works great. This one, the answer is no. This one doesn't factor any further because it's x squared plus 13. That doesn't factor any further. So that's completely factored form. Property here tells me that this can be, well, one of these factors has to be 0. So if you remember, the 0 factor property looks like this. Either that's 0, so x is 2, or that's 0, so x is negative 2, or this is 0. That's a little more to think about. That means x squared equals negative 13. That was one of those complex number deals right here. That's not a real number. But here's a little thing about imaginary units, or we haven't seen that in a while. So it's a little review of all this little stuff. Square root of negative 13 is I. Well, I radical 13, or minus I radical 13. Those are also x values that turn into solutions of this. Now, wrapping this up though, those are just the x values. We still need the ordered pair that works in this, so we still got to go back and get the other pieces, the rest of the ordered pair on all this. So I'm running out of space on this, but let me fit this in. I got to substitute each of these x's back in to see what the y is that goes with it. I'm going to use this expression for y. It was my original equation. Y has to equal x squared plus 4. That was the expression I used back here. So that tells me y once I know what x is. So using that, if you plug in 2, you get 8. So this is the ordered pair 2, 8. If you plug in negative 2, that's still 4 plus 4 is 8. If you plug in one of these things, well, x squared is negative 13. So you end up with negative 13 plus 4, which is negative 9. So I square root of 13 goes with a y of negative 9. And negative I square root of 13 goes with a y value of negative 9 also. So we will see a few of those nonlinear systems that end up with complex number solutions like that. That doesn't show up on your graph because we don't graph complex numbers. We only graph real numbers in the xy plane. These two things fit with our picture, negative 2, 8 and 2, 8. If you remember our picture, that looks like these 2 points. That's fine for this. We'd have these 2 points up here in the mirror image, negative 2, 8. And 2, 8. Those are the two that show up on the graph. And then you have a couple of non-real solutions involving I. And that'll happen with some of these equations. That's a little extra practice on it. So we're going to review a lot of these algebraic topics just in that one problem. You got graphs of parabola, graphs of circles, substitution method, which is new, polynomial algebra and factoring and solving polynomial equations, right? All of that stuff, and the complex numbers, all in there. We could have used quadratic formula on this one instead of square root property, but either way, you're getting square root of negative involved. So tons of practice on the algebraic stuff. So that's a nice way to end up the semester. Hopefully trig is fresh in people's minds. And the exponentials and logs wasn't that long ago. This stuff we got to review in this chapter at the end. This topic that we tackle at the end gives us a chance to review a bunch of that stuff in a new context. So that's a nice way to spend the last week of the semester, as well as looking back at your old stuff, the test, all of the tests that you've done. We're about to do a final where we have to do a little bit of everything. So look back through those. The stuff that you did well on those old tests, you want to think about. You're going to remember how to do it when you see it now. You're going to remember the skills that you had there. And then the stuff that you didn't do well on those tests, make sure you get those things sorted out, because you'll probably see some similar exercises coming up on the final exam. All right, so if you are using the XYZ homework, you can go in there and find some exercises like this. I took it out of section 9.3. They do a little bit with nonlinear systems. There's not a bunch in there, but there's some examples in there you can look at, and some practice exercises on that. I think in our Lumen stuff, I think I have a section on that. The Lumen work I put together, I got systems of nonlinear equations and inequalities. I got some practice stuff there. We're not doing the inequalities part. We're only doing equations. So you can find some examples on that stuff too in Lumen if you're using that. Written up there. Let me know what questions come up. I will. Monday I'll be putting out the last homework assignment and some practice stuff on this to look at for getting ready for the final. See you all soon.